Right, we're back again, and this time what we're going to talk about is more qualitative molecular orbital theory. We're still going to do a little bit of calculation, that's for sure, but we're going to tone it down a bit from these detailed calculations and try to understand a bit more about molecular orbital diagrams as well. The first question is, which atomic orbitals can be combined to form a molecular orbital? In principle, if we have a lot of atoms around and they all have valence electronic orbitals, we could have a big computational problem, because we would have to take as our molecular orbital, our trial, a mixture of all these things, and then we would have to do a ton of integrals like we've been doing on some of these problems. And then we'd have to figure out what the coefficients are and solve the secular determinant. And then we might find that a lot of them are zero. So we've spent a lot of time calculating an integral and doing something that then amounts to zero at the end. Well, that's nothing new. That's how a lot of science, in fact, pans out. Most experiments don't actually work, and the few that do get published, and the vast majority that don't come out either as very interesting or very important get mothballed. Well, suppose rather than mixing in everything, we want to cut out a lot of the work, and we're willing to accept a less accurate answer. Because what we're trying to do is understand qualitatively the reactivity and structure of the molecule, and not so much to 3, 4, 5 digits, things like the ionization energy. In that case, we can dispense with a lot of the possible combinations, and we can just outright kind of say they are not going to contribute. And we have 3 qualitative rules that we're going to use. The atomic orbitals can come together to form a molecular orbital which is in principle delocalized over all the nuclei in the molecule if, number 1, the energies of the atomic orbitals are similar. Number 2, the symmetry is the same. That has a precise meaning, but for now we're going to take that in a qualitative vein, and you'll understand later on what that exactly means. And number 3, the atomic orbitals overlap at least pairwise in space. If at least A overlaps with B and B overlaps with C, A doesn't need to overlap with C, then A, B, and C can combine to form a molecular orbital. As long as the information can get from A to C somehow through some integrals, we're fine. We can combine them all together. Okay, let's do practice problem 30 here and look at these qualitative guidelines. Let's see if they make sense. So here's the assignment. Rationalize the 3 rules for atomic orbitals to combine into molecular orbitals. In other words, explain why they make sense without doing a lot of calculation. Okay, rule 1. As we saw with hydrogen, molecular hydrogen, for example, the LCAO-MOs often involve constructive or destructive interference. If the phases are right, there's a buildup of electronic density. If the phases are wrong, there's a node. The electron is not found there. If the interference is going to be meaningful, then the wavelength, in particular the de Broglie wavelength of the orbitals, must be the same. And that means that the energies must be the same. In other words, we can't really talk meaningfully of an overlap between a flea and an elephant. They're 2 different size scales. And atomic orbitals can have vastly different energy and vastly different size scales in the same way. and only ones that are similar can talk to each other. And so that is a rationale then for why the atomic orbitals should have similar energy. Doesn't have to be exactly the same, but they shouldn't be too disparate. Or when we do the calculation, what we'll find is that if we include them, that they come in like the 2s did with a tiny, tiny coefficient, and we aren't any better off. Okay, how about number 2? Well, by the same argument, they have to have the same symmetry. As I said, what this means will be made a little bit clearer later on in this 131 series. For example, if I have an S and a P, and the P's end on end, then, as I'm going to show you on the next slide, you're going to end up with an overlap of 0, because you're going to build up some positive here and negative here, and by symmetry the overlap is 0. And so there won't be any combining, because you're going to get equal amounts of positive and negative interference by symmetry. So on this slide 624, here it is, for example, if I take two s orbitals and I combine them in phase, then I get a buildup. So there's net overlap there, and they can interact and form a molecular orbital of symmetry sigma. Likewise, if I have S and I have PZ, like I might have in hydrogen fluoride, for example, because the PZ has the same symmetry along the internuclear axis as S, they're both round or cylindrical, they can combine. But if I have it end on end, like in the second line, like PY, for example, then there's an equal amount of positive and negative interference, which I've tried to show by shading, where the orbitals overlap. And so then it's 0. And so that explains that. And for the third one, we said, well, they have to overlap at least pairwise in space. That's best demonstrated by this lower electron contour for lithium dimer using the 1s orbitals. So the 1s, by the time you get to lithium, are considered core electrons because they aren't in the valence shell. We're starting to occupy the 2 shell. These are 1 electron, 1s shell, the K shell. And lithium has a +3 charge, which is much bigger than hydrogen, so this 1s is pulled way in. It's like being on Jupiter rather than being on Earth. They're pulled in very tightly close to the nucleus. And you can see that if I try to take a linear combination of ++, which I've done on the left hand, the sigma G 1s, and then +- the sigma U 1s, they're virtually the same. Because if they don't actually overlap in space, if they don't interfere, then whether I take +- or minus+ when I square it, I get the same thing because they're completely separate. So there's a little bit of a contour on the left showing there's a little bit of something there, but that's not going to be enough to hold lithium together. That would be not completely insufficient to say that that's going to do anything to the bonding. And so for that reason, we just discount all the core electrons. We just assume if they're core electrons, they don't overlap in space, and we throw them out. And of course, chemists have always understood that it's the valence electrons, the ones in the shell you're filling up, that dictate everything about the chemistry, and that's of course why the periodic table is periodic. By contrast, here on slide 626, I've taken from Macquarie's excellent book on quantum chemistry 2 contours for the 2s, and the 2s do overlap, and then the total on the right shows you the overlapping of the 2s orbitals building up, and then the 1s is a tight, like a ball of yarn, and it's the 2s that are holding the thing together. And lithium dimer does form, of course, but it's not what I would consider to be a strong bond. Now, our qualitative molecular orbital approach can predict qualitatively whether simple homonuclear diatomics will be stable. By stable, we mean they're going to have a bond order that's bigger than 0. And by this rationale, for example, if we take our simple MO diagram with the 2s, it's very similar to hydrogen. With the 1s, we have the same bonding and anti-bonding. We predict that lithium-2, Li2 is stable, but beryllium-2 would not be, because beryllium-2 would be like helium. It would have 2 in the bonding, 2 in the anti-bonding, and so beryllium should not be, beryllium-2 should not form, or at least not strongly. We could probably produce it under special circumstances if we wanted to, but we don't predict that that's going to be an energetic bond to break. However, we can't predict just on taking 2 atoms. We can predict whether the 2 atoms are stable compared to being atoms or not. But unfortunately, for the study of condensed phases in materials, which is much more interesting from a chemistry and electronics and photophysics viewpoint, we can't predict anything at all about condensed phases from this kind of analysis, because the problem is that when you have a bunch of atoms, they don't have to just form dimers. They can form some other structure which you didn't ever bother to calculate, and which has a much better molecular orbital diagram and much better stability than whatever you did calculate. And so you can predict, for example, that C2, carbon, should be, quote, stable compared to 2 C atoms. It should have a non-zero bond order and so forth. However, neither graphite nor diamond nor buckyball nor graphene is organized in that way, and that's just because if you have more atoms around and you make a bigger molecular orbital diagram with those structures, what you'll find is that they're much more stable than C2, and that's why you get them instead. On the other hand, N2, which you can figure out quite easily from the MO diagram, is in fact the form we find in the atmosphere. It is a dimer. It doesn't form any condensed phases. And it's interesting that just moving one electron and one proton one way or another makes such a huge difference in what you actually find in nature. So let's include here the 2s and 2p orbitals, and the 2p are higher in energy, and if we're talking about a diatomic with 2 equal atoms, then the energies are the same. As I remarked before, if the atoms are different, then we have to keep in mind that the one that has more protons is going to have the energy levels pulled down for the same numbering compared to the one with less protons. And therefore, what I've shown here is kind of a generic diagram. It might be appropriate for O2 and F2 and a few others. There's a good and bad combination of the 2s. There's a good combination of the 2pz that's overlapping. All those have sigma symmetry. There's the py and the px, and that forms 2 pi orbitals. And then there are 2 where they're out of phase. Rather than having the lobes add up, they're the other way around. Those are the 2 anti-bonding pi orbitals. And then there's one where the 1p has got the wrong sign compared to the other one. There's a big node, and that's the 2pz sigma star, which is usually on the top of the diagram as the least stable molecular orbital. Now, energy is on the y-axis always in these diagrams. And you should understand that no matter how the diagram's drawn, you can't trust it unless you actually calculate the energies. And if you're going to calculate the energies, then you're getting into a lot of computation. So if you just want to draw something, that's fine, but you can't trust it too much if you actually want to figure out what actually is the case, because even in atoms, we calculated the exact energy eigenvalues for the hydrogen atom, but by the time we got to cesium, the 6s was in lower energy than the 4f, and they were all jumbled helter-skelter, and it would take a lot of calculation to actually figure out what those energy levels were. It's much worse, of course, with molecules, because we've got many centers of positive charge, the integrals are worse, and there's a lot of work involved. And so sometimes these things are just a very qualitative guideline, but you mustn't trust them too literally and be surprised if, for example, you change the atomic number and the whole diagram changes, because that even happened with atoms. And sometimes the energy differences between these things are pretty small, and so you just change one thing and this goes below that and that goes below this, and when you first start out, of course, that can be a bit daunting, because you think, well, I'm never going to figure out which one's below which other one. But there are some qualitative ways, we'll see in a second, that we don't have to do too much calculation. Of course, in reality, we saw by our calculation about polarization, the 2pz always mixes with the 2s to some extent, and it just depends on what the energy difference is between them, how much the mixing is. The orbital energies, whatever they are, is going to depend, if we did the calculation, on big R, the internuclear distance. And big R, at the minimum, where we're going to order the orbitals, because we're interested in what it is when the situation is the most stable, is going to be different. For example, N2 has a much tighter bond than O2 and then F2. And so just the fact that big R changes will change which orbitals can overlap and in what way, and that may have a big influence on what the energy ordering is, for example. And so therefore, don't be dismayed if the MOs in molecules appear to be jumbling around. That's par for the course. You would be amazed if they did not do that. And sometimes they jumble around just if you pop in a few more electrons and keep everything else the same, because why? Well, big R changed, and then the one that was so favorable before is not. And so it's occupied, but it now has a different energy. And in any case, the exact ordering is always going to depend on the molecule in question. Well, in freshman chemistry, we drew Lewis structures of all these guys, and we decided that N2 has a triple bond. That's why N2 is so inert and why it's so difficult to fix nitrogen. We spent a lot of our energy trying to take nitrogen, dinitrogen, out of the atmosphere and turn it into ammonia by a real hammer and tongs process, and it takes a lot of muscle to do that. Why do we want to make ammonia? Because usually we want to make fertilizer to grow crops, and we don't have enough otherwise. If we didn't have fertilizer, try growing things without it. And if you want to rely on organic fertilizer only, then you need a ton of animals, and you need a way to handle all that stuff and make sure it's safe as well. So let's draw in the molecular orbital diagram and fill in the electrons, and let's come to some conclusion about whether we would expect a single, double, or triple bond based on the bond order. I mean, the bond order should agree with the simple Lewis predictions. However, for oxygen there is a wrinkle, and in fact that wrinkle is one of the major triumphs for the molecular orbital approach, and that is that the molecular orbital approach predicts for sure that oxygen will be a diradical with two unpaired parallel electrons in different orbitals, and that can't be predicted by a conventional Lewis structure. So let's fill in the oxygen MO diagram. Oxygen has 6 electrons. It's in group 6. So there are 12 total, and I filled them up. 2 in the bottom, 2s sigma, 2p sigma, and then another pair and the 2p pi. And then the 2p pi star, the 2 anti-bonding side by side, out of phase, either this way or that way. The electrons in molecules are just like the electrons in atoms. If they don't have to pair up, if the apartment is the same cost and you can have your own place, then you take your own place. And so since these orbitals are exactly the same energy by symmetry, the electrons occupy them, and then they tend to have parallel spins because of the magnetic effect between them, and Hund's rule saying that the state with the highest multiplicity lies lowest in energy. That bond order comes out to be 2, but we definitely predict that these electrons are going to be unpaired in oxygen. And the question is, well, what effect could that have? And the answer is a lot, because if the electrons are unpaired, that means that the material is paramagnetic, and that means that magnets will interact with it. There'll be magnetic forces on these unpaired electrons. If all the bar magnets are paired up, then you can imagine there aren't going to be any magnetic forces. So this prediction that O2 is paramagnetic is one of the major triumphs of the molecular orbital approach, even for these very simple systems. If we draw the Lewis structure, we draw pairs of electrons, the oxygen, a double bond in between. We find out that, of course, the octet rule is satisfied, everything's hunky-dory, but there's no way we can look at that structure and say that it's going to have a completely different magnetic property or different reactivity than another molecule that has the same kind of Lewis structure with either 3 lines like nitrogen or fluorine, and both of those, of course, are diamagnetic just because the orbitals happen to fill up that way. So let's have a look here. I've taken a screenshot from an excellent video, which I've put on the bottom of slide 633 if you want to watch it. It's really amazing and beautiful to me how people have spent time making videos of interesting things like this. What you can see here is 2 pole faces of a magnet, and they're quite close, and they're holding some steel balls together to make a tighter space. And then what they've done is they've poured liquid oxygen through the space in between, and the magnetic force is strong enough that until the oxygen heats up and boils off, as long as it's a liquid, it'll stay suspended in between, and you can see clearly that it's sticking to the magnet. If you pour, it's a clear liquid, so there's no other indication. If you pour liquid nitrogen, which is also a clear liquid, through, then what you find is that it pours right through. There's absolutely no force on it at all that you can detect compared to gravity. Whereas as long as you get the pole faces close enough, which is why I think they put the steel balls there, you can suspend liquid oxygen there and watch it boil off. So oxygen is paramagnetic, and the MO approach is correct. Now there is a form of oxygen you can imagine, instead of having the 2 electrons paired, and keep in mind they're in different orbitals. So they're very disorganized. That's really lucky for us, because oxygen would be extremely reactive if, in fact, they were paired and in the same orbital. And that species of oxygen is so-called singlet oxygen, because the term symbol is multiplicity is a singlet. And you can make that. You can make that by decomposing various things that contain oxygen. And if you make that molecule, what you will find out is that it is an extremely vicious oxidizing agent. very, very fast. In fact, almost anything, if you immerse it in an atmosphere of singlet oxygen, bursts into flame. Paper, wood, on its own. Okay, it just starts reacting, heats up, and then they're so exothermic, it's off. So the National Enquirer would be right. There would be spontaneous human combustion if we had singlet oxygen. And it looks and behaves much more like fluorine, F2, which is another very vicious oxidizing agent. So in a way, once the electrons pair up and oxygen can get its act together, that's when it shows you its true colors. It is a very, very strong oxidizing agent. By the way, our immune system is onto that trick, and certain immune cells, certain attack cells, do in fact produce singlet oxygen and create it right near a bacterium and say, here, small guy, try a little bit of this to brighten your day. And of course it reacts with the molecules in the invader, and it's like a Molotov cocktail. That might be all she wrote for the invading species. Now on slide 635, here what I have is the difference between oxygen and nitrogen. So in nitrogen, the MO diagram looks more like this here. The difference is that these orbitals, the bonding orbitals in the P in both of them are all filled, but the ordering is different. The pi is lower, the two like this are lower than the sigma. And in oxygen, the sigma was definitely lower. The question is, why is that? What's the rationale for that? And the difference, of course, is big R. Nitrogen's very, very compact, tight molecule. Oxygen has a bigger bond distance between the atoms. And of course, the atomic orbitals themselves can be different. So there is a qualitative rationale for this. I'm not sure exactly how accurate it is, but I'll tell it to you anyway. And here it is. When the bond is short, or when the nuclei are small, like boron or carbon, which seem to have a similar MO diagram to nitrogen, then the overlap with pi symmetry is better than the overlap with sigma symmetry, and that lowers the energy, because when you overlap better, then you put more electron density between the two positive charges. That's a lower energy solution. The PZ may actually stick out the other side. So here's the idea. Normally I would have two red lobes here, and they'd be coming in and they'd be overlapping, and if the nuclei are out here and the lobes are like that, that overlap is going to be very effective. But supposing the nuclei get too close, like this, then as I've shown here on the bottom of slide 636, the red sticks out past the other nucleus into the blue of the other p orbital, and vice versa. And likewise, in between, there's not so much chance for the red to pile up a big intensity because it's going out and it hasn't quite maximized yet. And so for that reason, that PZ orbital, when the bond gets too close, may be a higher energy solution. But the side-by-side always gets better, right? So the side-by-side, the closer you get, the better it looks. And finally, if you're quite close, that could be superior then to the sigma, which is sticking out the other side. This is no substitute, I would say, for a proper calculation of what's going on, but it's much better than nothing at all and just saying, well, the energies just move around at random and there's no rationale at all. But we shouldn't take this qualitative stuff too seriously. Now, can we test any of this? The answer is yes. We saw that light was a photon in one of our early lectures, because why? We did an experiment with a metal surface and we ejected photoelectrons, which now we know are coming out of the atomic orbitals of the metal. And we can likewise take a gas like N2 and we can shine photons at it. And if the photons are energetic enough, there's a chance that they will knock an electron out and make N2 plus. And then if we measure with an energy analyzer the energy of the electron that comes out of the photoelectron and scan our energy analyzer, we will get a certain number of counts at various energies. And where we get a lot of counts, that means that we're actually putting in a photon that's ejecting an electron from an orbital, and then the leftover is what we're seeing. And so we can back calculate, knowing the energy of each photon and knowing that one photon ejects one photoelectron in the experiment, what the binding energy of the MO was. And so we can scan down and we can eject the top electron, the next one down, the next one down, the next one down. And this is so-called UV PES or UV photoelectron spectroscopy. We usually use an ultraviolet source because an ultraviolet source is much more effective at ejecting electrons. If we don't use enough, if we have red light, then we just don't eject any photoelectrons because we don't have enough energy. And of course that's the same reason why UV light from the sun, some of which does filter down even after it has gone through the atmosphere and the ozone layer, can be damaging to your skin because it comes in and it starts ejecting electrons from various molecules in your skin, and your skin tries to repair itself, but over time there could be some damage that can't be repaired. And if you get too much sun, by the time you notice the damage, it's sort of like trying to turn around an aircraft carrier. By the time you notice that you're steaming into port and going too fast, it's too late to stop. And so the time to stop the damage is early on, and if you live in Southern California like we do, the best solution is to wear a hat. And that's because as your hair gets thinner and thinner, you may put sunscreen on your face, but very few people put sunscreen on their scalp as long as they still have hair because it's too messy. And so unbeknownst to them, they get a lot of sun on the top of their head. And if they have something going wrong, unless you're inspecting yourself all the time, you may not notice it until the doctor says, well, that has to come out. That has to come out. If we assume Koopman's theorem is sufficient, remember what Koopman's theorem was. That said that we could just use the same orbitals we'd figured and use the same ones for the ion as the molecule. And of course, that can't be quite right, but it could be close enough to analyze things. If you assume Koopman's theorem is okay, then the actual readout of the photoelectron spectrum is just telling you exactly what the energy of the molecular orbital in the molecule was initially. And that's of course very powerful because we can calculate that and compare with the experiment. In fact though, of course, when you eject an electron, if that electron was involved in bonding, then it's like cutting a spring. The thing goes wild because it was held very tightly when the electron was there. Now the electron's gone and it's held with a much looser spring and it's way too tight and it starts going into vibration, and we can see that in the spectrum. So if we eject a certain electron, that there's a lot of vibration going on afterwards, what we can conclude is that that electron was extremely important for bonding. If on the other hand there's hardly any progression, then we can conclude that that electron was not that important for bonding. So here is a UV photoelectron spectrum for nitrogen, molecular nitrogen, and I've labeled the bands. There's P sigma near 16 electron volts, P pi, which has a long vibrational progression, and then there's P sigma star, which was down below. we see clearly that the P sigma, the PZ, is higher in energy because it's easier to eject than the P pi. So that establishes that the ordering that we've got for N2 is correct. If we did O2, which is more complicated because the electrons are unpaired, we'd find that the ordering was the other way. And then below the P pi is the P sigma star, which is the S combination, up almost near 19 electron volts. So as I've reiterated here on slide 640, the long vibrational progression, you see the series of spikes, tells you for sure that it's the P pi electrons that are doing the lion's share of the bonding in N2 and not the P sigma. Okay. Now let's talk a little bit about hybrid orbitals, because if you've had a course in organic chemistry, you spend all your time talking about sp2 hybrids, sp3 hybrids, this and that. Where did they come from? We haven't really systematically talked about them in any detail. But shortly after the Heitler-London 1SA, 1SB plus 1SB, 1S, shortly after that paper came out, Linus Pauling proposed a systematic way to rationalize Lewis structures. So Lewis structures were in the teens, 1916, 17 in there, and then quantum mechanics comes in, and then they could understand bonding, and now they still liked Lewis's way of drawing things with pairs of electrons and the octet rule, and that rationalized a lot of chemistry. And nobody wanted to throw that completely away unless you absolutely had to, because it seemed to be extremely useful to understand things. What Pauling proposed then is each bond or orbital takes a pair of electrons. That's the same as Lewis. And the bonds are localized between two atoms. If I have an atom here and an atom here, I can have a bond between them. But that's it. That's why I draw a line between them, and I don't draw the line snaking around over here. In the molecular orbital approach, we can't think of things in terms of those lines holding things together like that, because we have to first put in all the things and then solve it. It may be that certain bonds, molecular orbitals, are formed almost entirely from the atomic orbitals of the two partners. But it doesn't have to be that way. It's not a precondition. Then when you draw a line, you're putting a pair of electrons in there, and you're saying that the pair of electrons glue the nuclei together, so to speak. But Pauling was able to go much further than that, and that's because he was able to also explain the shapes of simple molecules. Why did they have the bond angles they did? Why were certain molecules planar and other ones not? And the structure of some of these were known, of course, but the bonding, the rationale in terms of the chemistry, was not very well understood. Methane, for example, is tetrahedral, CH4. This is probably going to be a review, but let's review it anyway. So here's what went on. Pauling wondered how, if you had carbon and 4 hydrogens, why you got a tetrahedral structure. And in particular, you know what the valence orbitals for the carbon atom are. You've got a 2s, which is round, and then you've got 3 2p's that are all at right angles to each other. And in methane, the bond distances are all identical, and the bond angles, HCH, are all 109.5 degrees, the tetrahedral angle. How can we do that? Well, let's look at the valence shell electron configuration of an isolated carbon atom. It's 2s2, 2p2. And the 2 electrons in the 2p are going to spread out because the 2p in the carbon atom have the same energy by symmetry, and therefore they're going to spread out and have the same they're going to be parallel spins. The s electrons, though, the s shell's lower, and the 2 electrons in the s shell are paired. And so there's no hook there. A hydrogen comes up with 1 electron to that 2s shell. There's nothing that can happen because it's filled. And so it could just bounce off. I'm not going to get a bond to form there. I could get a bond with 1 electron from the hydrogen and then another one from one of these 2p, but I've only got 2 of them. And therefore, naively, what you would expect is you would expect to find CH2. And you would also expect that the 2 hydrogens would be at right angles. One would be 2px, let's say, and one would be 2py. And we don't find CH2. I guess you could find it in a flame, in a combustion reaction, but you certainly it's not the stable form. CH4 is the stable form for sure. And the bond angles are not 90. Here's the way Pauling then explained what goes on. First, making a molecule is like starting a business. And when you start a business, you have to borrow a little money usually, because otherwise you can't get going. And so what we do to start this molecular formation, at least in our minds, is we take the initial stable configuration, 2s2, then the 2p, and we grab one of the s electrons and we move it to the vacant 2p. That's borrowing energy. That's like borrowing money. We've got to pay that back. But now, after we borrow, we've got 4 half-filled orbitals. And that's great because we've got 4 hydrogen atoms coming in. That's exactly what we want. Now, still though, I've got no go because I've got 4 of these orbitals, but one of them's an s and 3 are p. And so if I just naively combine each hydrogen with 1 orbital, then they aren't going to all be the same. And because the s is round, I'm kind of at a loss as to where to put that 4th hydrogen anyway. Where should it be? And the other should be at 90 degrees still. So that's not going to work. Therefore, what we have to do is we have to somehow combine these orbitals into orbitals that are all the same. And since there's 1 s and 3 p's, all of our combination should be 25% s and 75% p, and that's why they're called sp3 hybrid orbitals. They point also at the positions where we find the hydrogen atoms, but it's kind of an interesting mathematical point in that if you don't orient where the hydrogen atoms are in a very clear way, then it takes you a long time to figure out what the hybrid orbitals are. So let's have a look then. Here are the 4 starting orbitals. These are not meant to be quantitative in any way. These are just drawings. But there's a round one and there's 3 dumbbells at right angles. And I've taken the 2s to have positive phase, so I've colored it red, and the others have positive and negative phase, as shown. And now what I want to do is I want to put the hydrogens where I know they are, because I know it's a tetrahedron, and then I want to figure out how to make 4 orbitals, one of which points at each hydrogen to make a bond. The key is to draw a cube, like I've drawn here on slide 646, and to put the hydrogens at the corners of the cube. On the top corner, you pick kitty corner one way, and on the bottom, you pick it the other way. And that's ever so much easier than the usual way you might draw of putting 1 straight up and then 3 down, like this as a tetrahedron. This makes it much clearer to see. I've colored the 1s orbitals around the nuclei of the hydrogen red just because I'm going to pick the positive phase. I'm free to pick any phase I want. Now, to make a bond, if the hydrogen's red, the carbon's in the center of the cube, What I need to do is take a combination of those guys so that I get a red thing pointing at the red thing that's the hydrogen. Then I know they can constructively interfere and 2 electrons can slot in there and I can get a bond. And that's the idea then behind the hybrid orbitals. So what do we want for HA? Well, HA is 1 unit in X in the positive direction, 1 unit in Y in the positive direction, and 1 unit in Z. So that's the first hydrogen, HA. To make a hybrid orbital on carbon, the correct combination to point at that thing is to just take C2S, that's round, so that points nowhere, and then add PX, points in plus X, the red's over here, PY, now the red's over there, push it up, PZ, now the red's pointing right at that hydrogen marked HA. Therefore, that's the correct combination to make a bond with HA. And I've got 4 of them, and I can easily then take the others and make bonds. So we can get the others for HB, which has X negative and Y negative. I just changed the sign of the p orbitals. So for HB, it's C2S minus C2PX minus C2PY plus, because it's still up, it's kitty corner, C2PZ. And then for HC, there's another combination. The minus signs move around so that it goes to that corner. And then for HD, the minus signs move around again. And in fact, you get all possible combinations. One of them's all plus. All the others have 2 minuses at least in the formula. Exactly 2, in fact. And that then gives us 4 combinations. I started with 4. I end up with 4. But the 4 I end up with, mathematically and now, are all identical. And mathematically, they point at the tetrahedral angles. And therefore, I predict that with this theory, that I'm going to have 4 equal bonds, and they're going to be at 109.5 degrees. Now, the question is, what happened to the energy we borrowed? What happened to that? Well, we borrowed energy to unpair the 2s electron and promote it to the 2p, but now we get all that energy back and more, okay, because we started a successful business, so to speak, and we made 4 very nice, strong bonds between hydrogen and carbon, and that is a winner. That's exothermic like crazy. And so that then allows us to recoup the energy that we borrowed plus more. And so that explains how that could in fact happen. So we get CH4 and not CH2, and we get 109.5 and not 90 degrees. The carbon orbitals, of course, whatever they are, they have some complex mathematical form. We haven't solved for them. We just drew some qualitative shapes. But whatever they are, they're normalized, that's for sure. And so they're all normalized. Integral of 2px squared or 2s squared is 1 over all space. And they're all orthogonal. So the 2ps is orthogonal to 2px, and I think you can see that by symmetry. Those integrals are all 0 because one of them is positive. And of course, if they're at right angles, the 2p's, the integral is 0. That's easy to see as well. That lets us normalize our Pauling hybrids. We have to take, let's take our first one that points at HA. We've got 2s plus 2px plus 2py plus 2pz, quantity squared. We end up with 16 terms, but 12 of them are cross terms between s and p, and I don't have to calculate those. I know they're 0. And the other 4, conveniently, I don't have to calculate either because they're 2s squared, which I assumed was 1. And so we get 4 that add up, and they add up to 4, and that's the end of the calculation. and therefore we divide each hybrid by 2. I can make then the first hybrid, I can call it phi A, that points toward that hydrogen. It's 1/2 2s plus 2px plus 2py plus 2pz. And I can normalize the other ones the same way. There are other hybrid combinations, and they're derived in exactly the same way. If I've got an S and a P, then I can take S plus P or S minus P, roughly speaking, and I can get something that pushes a positive red lobe one way or a positive red lobe the other way. And an atom that's hybridized like that will make bonds at 180 degrees. That's like acetylene, for example. If I have 2 P's and an S, 2 P's is a plane, so it's going to be planar. The S has no direction. So sp2 hybridized would be at 120 degrees when you work out the 3 combinations. And planar, sp3 is tetrahedral. And then to explain transition metals, if you get very enthusiastic, they can have 4 and 5 atoms stuck around the metal. Often they do. And you run out, so you say, well, if I run out of S and P's, let me throw in some D's. And you can actually, they're very hard for me anyway to see and draw, but you can take a D and you can add a D to the sp3, and now you've got 5, and that can make a trigonal bipyramidal, something with a north and south pole and 3 sticking out in the equatorial plane. And you can take D2 sp3 hybrids, and you can make an octahedral structure that has 2 at the north and south pole, 2 here and 2 here. And that's, I don't know how much reality I would put into those orbitals. I think at that point you're playing a bit of a mathematical game rather than a realistic description of the bonding. But anyway, historically that's one way to rationalize how you can get those other stable structures and why they have the geometries that they do. And all these hybrid orbitals match the qualitative valence shell electron pair repulsion, which just basically said the electron pairs around a central atom are sort of like electrostatic charges, let's say. They just repel each other and they try to move apart as far as possible. That's the qualitative VSEPR approach. Okay, next time what we're going to talk about is why Pauling's approach is in fact falls short even for methane.